Thanks very much for having me. I'm really excited to be here today with, hopefully some of you met Dr. Chris Versteeg, who's a postdoc in my lab. So thanks very much, Sabera and Mary and all the organizers. This is such a great idea and awesome opportunity to come see Caltech. I've never actually been to campus, so this is a lot of fun. So for this introductory lecture this morning, general topics I'm covering, intro to deep learning and intro to neural population dynamics. I think there should be a fair amount of overlap with things that you've heard in the last week. From my standpoint, I don't mind if there's repetition. I think it's really helpful to keep building intuition, and then we're going to dive in pretty deep in the methods lecture this afternoon. So I think it's hopefully you'll see a lot of things and you'll be wondering, like, have I seen this before? The answer is hopefully yes, or at least something very similar. So what you'll hear about in this lecture today, we'll just go over basics of neural networks. We'll talk a little bit about deep autoencoders. So I think you've already gone over autoencoders a little bit, and we'll extend that to deep networks applied to autoencoding. And then I'll kind of round this out with an intro. It's going to be a completely different topic, really, an intro to neural population dynamics. And hopefully you'll see in the later lectures how these things tie together. This is meant to be pretty informal. If you have any questions, feel free to raise your hands at any point, or just start talking. And I don't mind being interrupted. We've got lots of discussion time later, so there's no problem kind of going over time-wise. So let's start with some basics of neural networks. Okay, we're starting with some very basics here. So hopefully this looks familiar. So the idea of an artificial neuron, this is tracing back to McCullough and Pitts, like back in the 40s. The idea of an artificial neuron. So this is maybe like one of the times when neuroscience actually kind of heavily influenced AI, at least at that time. This is like kind of a neuro-inspired architecture where you have this kind of functional unit of computation, the artificial neuron. It takes in various inputs, so we can think of the input as a multi-dimensional vector, so x, which has dimensions x1 through n. Cool, very AI there, appreciate that. Okay, so it receives some number of inputs. It multiplies those inputs by a corresponding number of weights. So for every input, there's a weight that is summed together. There's a bias term typically that I'm leaving out here. But then, multiply, sum, and then pass that through an activation function, and you get the output of the artificial neuron. Is this generally familiar to people here? Oh. Okay, great. If you're lost already, now's a good time to interrupt. Okay, so general idea. This is obviously a very kind of generic framework. Again, from McCullough and Pitts in 43. Maybe a side note is that so here's a case where neuroscience really inspired AI. Then I think they really diverged for many decades. There hasn't been a ton of neuro influence on AI, but some convolutional neural networks and stuff like that. But I think if that was kind of the neuro to AI arrow, I think the arrow is almost going in the other direction these days, which is what a lot of you are learning about, which is how is AI influencing neuroscience. Anyway, so the general idea here, again, you've got a function, you weight your inputs, you sum them, there's a bias term B there, you've got you pass all that through some function. That function can be nonlinear, and you get the output of an artificial neuron, okay? So how do we apply an artificial neuron? Let's think about a simple problem. Let's imagine you have data that are two-dimensional. So, remember I talked about an input data vector x. Here it's only got two dimensions, x1 and x2. And in this case, let's say it's a simple classification problem, meaning the data divide into two groups, green and red. And so green is class 0 and red is class 1. So how do we train, how do we train a model to do what we want here, which would be to separate these types of data? So, the solution here, this is a pretty easy problem. The solution is effectively like, intuitively draw a line that separates these data. So that would be what we'd call our decision boundary between, the two different classes. And then so orthogonal to that line is a vector, okay? If you take these two-dimensional data and project them onto any data point onto that 1D vector, it'll tell you how far away you are from the decision boundary. Things that are, kind of very positive, you should want to be classified as green. Things that are very negative here, you should want to be classified as red. But we've boiled down this classification problem into just like, projecting onto a vector that's effectively a dot product, and then just deciding, depending on the sign of that vector, whether you're in class 0 or class 1. Okay. So how would an artificial neuron be applied to this problem? Very simple. Again, x1 and x2 are your inputs. We need to learn some weights, w1 and w2, sum them together, pass them through a nonlinearity, and then the output of this should tell you whether you're in class 0 or class 1. So this input stage here is effectively that dot product, right? Projecting your data onto a one-dimensional vector. That would be what's happening at the input. And then the nonlinearity, in this case, this is like a sigmoid. Nonlinearity, that could be a variety of things. But actually, for this problem, you wouldn't even need it. It's linearly separable. You could just, have that be a line. Okay. But so this general architecture is called the perceptron. So it's like taking an artificial neural network, an artificial neuron, just one of them, giving it a bunch of inputs, and then let's say classifying, into two classes. So again, essentially for this type of problem, all we really care about is knowing whether the data are above or below this line. That's kind of a one-dimensional property of the data. So all we need to do to figure that out is to dot product the data with this vector. All good, everybody? Everybody on board? Okay, so that's pretty straightforward. You think like, why do I need an artificial network for this? I could have just drawn that line myself, y equals mx plus b, figure out what's orthogonal to that, and then, this problem is easy, it's done. What about a harder problem like this? So now let's imagine, this is a kind of a very different data distribution. Once again, we have two classes of data, like red and green, but there's no line I can draw here to separate out these data, right? Any line you drew, if you said, all right, separate out into like above and below the line, well, here these red points are going to get misclassified because they're below the line, and some of those green points are going to get misclassified. There's no line that'll do better because these data are not linearly separable. By the way, these slides are kind of a mix of things taken from blog posts and as well as like actual references, but I should have links at the bottom of the slides if you want to look up sources. But okay, so this is kind of a key point. As problems become more and more complicated, linear approaches can start to fail. And so simple linear classifiers like the perceptron just wouldn't quite do it for these types of data. And a lot of real world data, look at this. This is only like a 2D problem, and already like a simple perceptron can't handle it. So one strategy we can use is to pass the data through multiple successive transformations, so we can change kind of this nonlinear, hard separability problem into a more linear problem if we can kind of transform the data. And this is where something like the what's called the multi-layer perceptron comes in. And this is from parallel distributed processing, Rumelhart, Hinton, Williams. Just the idea to take the same perceptron we've already talked about and string them together. And if you guys are maybe a little bit familiar with deep neural networks, like that's what we're talking about here. It's effectively like we've gone from one layer to multiple layers. And the idea is through these different layers, maybe these data can kind of be warped so that by the time you get to the output, it's easy to linearly separate them. Does that make sense to everybody? Any questions on that?
Like, when do you decide it's not good enough? So you said like 5.
Yeah.
I mean, yeah, it wasn't perfect, but it was kind of good, it's like 90% of the job.
Right. Yeah. No, good question. I mean, I think there's always right, this trade-off between kind of how complex do you want to make your model versus like how high can you kind of get it to perform. And I think that's like on a problem by problem basis, unfortunately. Like you have to decide. The linear version of this was very easy to interpret, right? It's like we know what the system is doing, it's drawing a line, separate. So if you need to like kind of interpret the computation, that's super easy with linear methods. Once you get to deep networks and they get harder and like deeper and deeper, many successive transformations, yeah, it becomes much harder to interpret. So I think there are methods to do that, but I think you obviously don't want to make your model more complex than it needs to be for your goals. These deeper networks are generally capable of anything that the simple model can do. Right? Like the deep network can also do it. So there are ways of kind of training the networks. So I think the two maybe key questions are like, performance versus interpretability. That's kind of one axis. The other is as you start to have, deeper and deeper networks, more complicated models, so the W's here are the weights of these networks. The more of them you have, the more there is to learn, right? So you all of a sudden start to have more and more parameters that you have to learn, and you need more and more data to have to do that. So those, that's a case where, using a more complicated model could kind of shoot you in the foot because maybe you don't have enough data to actually, and there's plenty of ways to kind of regularize models to deal with that, but there's that trade-off with model complexity.
So are the transformations between each one of the layers the same as the single layer that's just 2 layers?
Right. So not quite, because if we took out this stage here, then these would just be linear transformations. It'd be like taking your data and multiplying them by matrices. And you can only, there's only so much you can do with linear transformations, as we talked about. So these nonlinearities are key because that's where the data can actually get warped.
You need the sigmoid, right?
So yeah, sorry, I think this is like, this isn't even a good nonlinearity, but yeah, like the sigmoid, you might have used like ReLU or ReLU, I don't even know what people call them, rectified linear nonlinearities. There are a variety of ones you can use, but the point is like that's where kind of the data can get warped. A bunch of matrices are just going to give you linear transformations.
Right. But I mean, in comparison to the single layer perceptron that also has the nonlinear transformation, I mean, is it the same? It just has more multiplication in the small layers.
You're saying like
compared to the single layer perceptron.
So I don't want to say anything too dumb, so I've got to be careful here. So like, I mean, I think what you're saying is like, if you have, can you take a single layer perceptron and
add layers,
or like with a deep network, like is there an advantage? Can you approximate any of those transformations with a single layer perceptron and a nonlinearity? I'm not sure about that.
Yeah, I mean, I'm asking a very dumb question, which is the only difference between the two kinds of networks.
Oh yeah, no, I'm sorry. Yeah, that's exactly it. So you're taking the output of this network and passing it into the output of these neurons and passing them into another set of neurons that look just like them. The weights are different.
Right.
Right. So we're learning different weights for each layer.
Different things as a function of the number of layers, I assume.
Yes. Yeah. So typically, like if you look at in image processing, you'd see kind of a hierarchy of complexity in the network as you go from like the earliest layers. They might be kind of certain types of feature detectors, like very simple features. Then as you go like further and further, you might see kind of like object detectors, which like if you looked at what those neurons are responding to, right? So yeah, exactly. There is kind of a hierarchy. Yeah.
I think to your question, I think it's been proven that if you have a single layer that is infinite, single layer that can do anything that arbitrarily deep network can do.
Right.
Which means that like deep networks are better, but like you could theoretically approximate any function.
Yeah, I believe that's correct, which is why I kind of am being very hesitant, because I mean, I think there are challenges to learning kind of I don't even know what like how you'd expand the dimensionality appropriately to do that, but yeah, anyway, agreed with what Chris says. Okay, so yeah, let's get a little bit more concrete about this. So let's say you have this multi-layer perceptron where you just have that same basic perceptron that we started with, and then you kind of put multiple of them in serial, and then the output is the final classification. So just a quick let's make sure everybody's on the same page. So what are the parameters of this network? Sorry? Yep, that's right. So at each layer, I only drew kind of one artificial neuron, but you might have multiple. Each one of those has weights. There's also bias terms that I didn't draw here, I apologize, but exactly the weights of each artificial neuron and their biases, which is just like a scalar addition. Those are parameters. Typically, we randomly initialize these. Like if you have a new data set and you don't obviously know what those parameters should be, so you typically like randomly initialize them. So then we want to learn parameters that'll make this network do what you want. So this should also hopefully be a little bit of review. What would be the objective here when you train the network? So what's the loss? You guys talked about loss functions at all? Cool. So yeah, please. Yep. Yeah, exactly. So yeah, like you've got a piece of data, it has some number of inputs, and then it has a label, which is like, is it from class 0 or class 1? And so the objective is to make the output of this network match, right? And so now how do we find the parameters? And I think this is where you might have talked about this a little bit, but maybe not in detail. But so, like I said, we randomly initialized these weights. We have a bunch of data. How are we actually going to find the parameters? So I'll just answer it. We're gonna use gradient descent. So I think you had a little bit of an intro to gradient descent, but again, I'm just trying to build some intuition here. So we'll go through it a little bit more. So let's imagine that this is your loss landscape. So we talked about what the loss was. It's like, how accurately are you classifying? In this case, this wouldn't actually be for kind of this type of classification problem. But the point is, let's imagine for a second that your model only had one parameter, okay? And you could try all values of that parameter. Then you would get a bunch of different losses for all those different values, right? And so this is kind of an example of what the shape of that curve could look like. High loss is bad, right? So the optimal value would be somewhere here in the middle, right? To minimize your overall loss, okay? So for neural networks, especially deep networks, how we typically, we're initializing randomly. We don't know where we are on this curve. I've drawn a blue line, but you don't actually have that. If you have one parameter, you could try every value, like do a grid search or something, try every value, and roughly say like, okay, here's the optimal one. But we never have one parameter in a neural network. If you only have one parameter, then you're doing something wrong. Like you shouldn't be using a neural network for that problem. Okay, so you can't actually know what the shape of this curve is, but you need to somehow find its minimum. So we use gradient descent, which is basically we guess a parameter value, or you randomly initialize, let's say. And we can evaluate the network with that parameter value. So that gives us some loss, and in this case, that's pretty high. But then we want to calculate the derivative of that loss with respect to that parameter. So that's the gradient that we're talking about. Okay, and it's really just the slope of this curve. So right, this is super simple. We have this curve. We don't really know its shape. We don't know where its minima are, but we just want to like locally say, all right, what's the slope of that curve? And then like once we know the slope, we know that, okay, going in that direction will make my loss lower, right? So that's just like a linear approximation. So we know that this, this way is pointed down, so let's go that way. And do it again, right? Evaluate the loss at this point. Again, take the slope, and just keep going kind of iteratively until we converge to the right value. Okay, so did that all make sense? I shouldn't have gone back, so now I have to go through all those builds again. Great. Any questions here?
Yeah, how many times do you need to initialize so you know, like
Yeah, great question. Let's cover that a little bit more. So, I think exactly what you're saying. So in this case, right, this is an easy problem. This landscape is like it's quadratic, right? So you know that there's like only one minimum. That's not the case in general, right? So like this process can easily get stuck if there are minima kind of along the way to the global minimum. Okay, so let's just first change this gradient descent. Oh, shoot, do I have to go through this again? Change gradient descent a little bit. So now let's imagine this is like a 2D loss function. So instead of the quadratic, we're now looking at a contour plot of a two-dimensional loss function, which still has a global minimum, right? So you could kind of evaluate the gradient at each of your points, follow the gradient down, and you'll get to the global minimum with this nicely shaped loss function. What's typically used in neural network training is something called stochastic. Well, not quite this, so we'll go a little bit more in detail, but something like this, stochastic gradient descent. So gradient descent, it's like you look at all of your data at the same time, and you kind of calculate the gradient with respect of the loss for that parameter with respect to all of your data. Typically, the way we train neural networks is in batches, meaning you don't actually evaluate all of your data at any time point. You'd sample kind of a subset of that data. And what that does is it actually gives you a noisy estimate of the gradient. And it sounds like, well, that's ridiculous. Why would you want a noisy estimate of the gradient? What that means is as you're kind of optimizing, you're bouncing around more, right? So each time you're drawing a subset of your data, you're not necessarily going in exactly the right direction, but you're generally going in the right direction. So it's slower than if you were to optimize using gradient descent and all your data. But to your point, if there were kind of local minima along the way, this type of noise helps you bounce out of local minima because the landscape is always kind of changing a little bit. Does that make sense? Again, not going through math here, just trying to build some intuition, but the key point is gradient descent is really nice if you have a nice landscape where you're guaranteed, if I just keep following the gradient, I'll get to some like optimal set of parameters. That's not the case in general. So we typically use stochastic gradient descent. There's a key thing I'm not covering in this lecture, and I thought about it for a while. I was like, there's just no way I can do it. I'm not telling you how to calculate these gradients. For a single layer, for a single like perceptron, it's pretty easy to calculate the gradient with respect to like each of those parameters. I'm sorry, the gradient for each of those parameters. But once you get into multi-layer perceptrons, you start to have to use backpropagation. And that I just did not have a way to go through the math for backpropagation in this lecture. So trust me that there are people on YouTube that give much better lectures about backpropagation than I could, and it's worth about half an hour of your time to sit through and kind of understand when you have a multi-layer, like a deep network, how do you actually kind of calculate the gradient for those intermediate values, weights, sorry. Okay, so I apologize for that, but all right, so now to your point, what if you had a more complicated loss landscape like this? So in this case, again, so here's kind of the loss as a function of your parameter value, and you start out here, which is not a great parameter value, but you're just guessing, and you want to get down there, but in between, you have this this local minimum, right? So If we just did kind of standard gradient descent, you would get stuck there. Even actually with stochastic gradient descent, you can get stuck. So there's one more key piece that I'm not going to go into mathematical detail on, but just again to build intuition, is optimizers that are typically used don't just use stochastic gradient descent, but they add things like momentum terms, which is like basically giving you some memory of which way you were going when you traveled down the loss landscape. So just as an example, this is, there's a nice tutorial on an optimizer called Atom, which is kind of like the workhorse of modern machine learning. Like every year there are like 7 papers that say that like, okay, we beat Atom, and then every year people still continue to use Atom because it's awesome and it works really well. So it's worth learning a little bit about. But so let's imagine that you kind of initialize your parameters here and use a couple of different optimization methods. You can see that stochastic gradient descent gets stuck here. Even stochastic gradient descent with momentum can get stuck. But a couple of the other ones, like, SGD with momentum did not get stuck. So like the optimizer itself would have gotten stuck, but it had some memory of which way it was going, and that allowed it to kind of push through that local minimum. And that's why SGD with momentum does make it all the way down to the bottom here. The thing is, it just takes a lot longer than Atom. So like this is a whole field of like how do you design these optimizers, how do you tweak them, but just to give you some intuition for what they're doing, they're trying to get past the problem that you were mentioning of local minima. Oh, sorry, yeah.
What if there are actually several local minima that are the same?
Yeah, I mean, I think so. In kind of modern deep learning, there always are. There are local minima everywhere, and so this is a little beyond my expertise. I don't understand how these optimizers manage to kind of blow past them, but I know like in practice for a lot of the networks we try in my lab, you can try a bunch of different initializations and often converge to very, very similar solutions. So it's a little bit surprising.
Yeah, so I think that's exactly the step. So if they are local minima that are the same, that means that it doesn't matter how much one you have.
So you want to, so this is what we call a local minimum, but we want to be down here, which is like a much better loss value.
But if there are several minima that are the same,
Oh, like down here. Okay, yeah, I see what you're saying. Yeah, so there's like, basically the exact parameter values don't matter. And that's definitely like the case in practice, that you're what we call over-parameterized, like meaning, there's redundancy there and it doesn't matter what final solution you converge to.
Yeah. Interesting. Actually, so like if you think about this code one-dimensional parameter space, so you only need to be at the local minima in one dimension for it to be like really bad for you. But it turns out when you have like billions of parameters that you are all tuning, you can imagine you're just adding more and more dimensions. And you only really need one to be sloping downhill in order for you not to be a local minimum. And so it's like actually an interesting feature, like when you expand the parameter space, it actually makes you less likely.
Right, there are more kind of paths to traverse down to a better solution. Yeah, that's a really good point. So, I mean, like related to that, again, this is the case where we would only have one parameter in our network. Like that, again, doesn't happen very often. And so here's a case where we've gone from like 1 to 2 parameters, right? So now X and Y are parameters and the Z-axis here is your loss. And I mean, this is again from the same blog, same idea that some of your optimizers are going to get stuck. In this case, different optimizers, like so Atom still performs well. RMS prop happens to get past the local minima much earlier than stochastic gradient descent. But key point is, again, this is all to build intuition, but typically we're talking about like this is for 2 parameters, a 2-parameter landscape. We're typically like for a small network talking about many thousands of parameters. For like modern, the stuff that you hear about in the news, those types of networks, we're talking about many millions to billions of parameters. So that means you've got a many million to billion dimensional landscape that you're trying to, kind of converge down to some minimum. Yeah.
In terms of the order of operations within the architecture, all of the optimization of each neuron's weight parameters happens at the same time?
Typically, so there's a lot of variance. I don't want to like kind of summarize, but like, kind of the naive approach of just like randomly initializing everything and kind of training everything at the same time often works pretty well in practice. There's a ton of like thinking about regularization, learning rates. There are all sorts of things that you kind of have to tune, but it's very often that you're kind of training everything in parallel. Maybe a conceptual kind of variant of that, I don't know if you guys covered this at all, is the idea of training a network for one thing and then using it for other applications. So that's usually called pre-training or transfer learning, where so then you might train the network in kind of one setting where you can like really robustly train a network, and then you might have like your own application that maybe you have less data for or something like that. You borrow parts of that network, don't change them, and then like change other pieces, or maybe like very finely change the weights of that one. Cool. Any others? All right. Cool. So yeah, I'm clearly going a little bit slower than I intended to. We haven't even gotten to topic 2 yet. Apologies. So we talked about, I was showing you kind of the multi-dimensional, like 2-dimensional data cloud. But in practice, a lot of the problems that we want to apply these networks to are much, much higher dimensional than that. So and what's nowadays like a really simple problem, but at least like 10 years ago was a hard problem, maybe 15, is recognizing handwritten digits. So let's imagine, so this is like, I think originally like, we send letters, you've got to, automatically figure out where the letters need to go. So you need machine learning systems that can classify handwritten digits from the letters. So we want to recognize like this image as a 3. But we also want this to be a 3. And we also want this to be a 3 and this, right? All of these things are a 3. And so think about kind of the dimensionality of this data. So this is, this is a really kind of standard, well-known data set, now kind of classic, called MNIST, where they have a bunch of like handwritten digits that have been labeled, so like an image and then the corresponding label of this is a 3. The dimensionality of this data is 28 pixels by 28 pixels. So even in this like classic simple problem, this is a 784 dimensional input, right? So data size, data dimensionality scales pretty quickly, right, with modern machine learning. And a key point with a problem like this is like, let's take these 2 examples of a 3. If you looked at any piece, in any single pixel location, the values are, like in that case, the 3 has a 0 at those, in that area, at those pixels. In the other case, the 3 has 1s or, is bright in those areas, but it's the same digit. And similarly, if you look at the bend of the 3, it can have like, it could be bright, it could be dark at those specific pixel values. So you can't depend on any kind of specific pixel values to solve this problem. And similarly, like there could be similarities to the 6, but like everyone in this room can instantly recognize that that's a 6, even though it's kind of like a high dimensional classification problem. So, how are these solved in practice? Sorry. So this is, I love this comic from XKCD. This is your machine learning system. Yep, you pour the data into this big pile of linear algebra, then collect the answers on the other side. Well, what if the answers are wrong? Just stir the pile until the answers start looking right. That's basically deep learning. I mean, that's not exactly, but like we were saying, take a network, randomly initialize the weights, jitter it around with some noise, optimize with momentum, you'll get to an answer. That's kind of how these systems work. So everything we were talking about with the multi-layer perceptron for the 2-dimensional problem, you can use kind of the same architecture now when you get out to 784 dimensions, where you have multiple layers, and then at the output, you have like the probability that this is a 0 versus a 1, etc. So the main reason I'm bringing this up is kind of it seems like a much harder problem, but conceptually, all that intuition that we were talking about in the beginning of the lecture, even for just a two-dimensional problem, it all translates. Like you could code up that first network, change the dimensionality, and you could still get this to work. I'm just this doesn't really matter, but I learn by visualization and intuition before I can learn math. So there's this great YouTube lecture series from 3 Blue 1 Brown on neural networks, and I find it really helpful. He'll in his series he goes through like backpropagation in a really like rigorous, but he builds a lot of intuition along the way. So here's just an example of him showing how like these deep networks work, where you take these pixel values, you have a 2D image, translate them, just turn them into a vector, pass them through like successive layers of your deep network, and at the output you have kind of the classification probability. Yeah, please.
I mean, you say intuitively it's the same conceptual, but here you need to choose like so many different functions for each layer.
Oh, sorry. So I probably was unclear when I was saying that. So the artificial neurons you're using, they're the same basic architecture, right? Like they take their input, they multiply them by weight, and they pass them through a nonlinearity. And you can just pick one nonlinearity typically. So like for all the layers. At the output, you might have to do something like a little bit specific. So like in this case, you want the output to be a probability, so that should like sum to 1 over at the end. But like that's they're very minor changes that you might have to do. But yeah, the architecture, like each one of these units is basically the exact same thing, right? Dot product at its input, nonlinearity, pass that output to the next layer.
Oh yeah, that's
Yeah.
what I was asking. Would that be enough?
Yeah, for a lot of problems, you can get away with just using this. And it's not like the nonlinearity often doesn't matter. Like people tend to use ReLU, but there's like soft plus and some other things that like they all seem to like perform quite well. So like we were saying, there's a lot of redundancy in these networks. There's a lot of solutions that all give you very similar performance. Okay. Yeah, so this was just, again, to kind of summarize, you're taking your 700-dimensional input, you're just passing it through that multi-layer perceptron that we talked about earlier, and you can do a really accurate job of classifying these digits even with that very simple architecture. But I just want to remind you that we've talked about landscapes in like kind of the 1 or 2-dimensional case. So at the input, you have 700, let's say about 700 dimensions. And then in the next layer, I didn't specify it here, but maybe you have 100 dimensions. So with that first transformation, how many weights are you learning? It's not 784, it's 784 times 100, because you've got the pairwise, right? Each one of those networks is seeing, every input from the previous layer. So you can see how the dimensionality scales before, where we were talking about 2-dimensional landscapes. Already kind of at the first layer of this network, you've got 78,000? No, 7,800 dimensional. And that's only for like one layer. But so think about this landscape, and then just think like 7,000 dimensions in your head, and it's all the same thing. You just need the intuition for how this works. Yeah, good? Okay. I just wanted to build, this part should be much quicker, but I just wanted to build off that a little bit to talk about, I think you've already talked about autoencoders. And so maybe we can think about deep autoencoders. So I think in autoencoding networks you covered already, it was probably kind of a linear transformation to get to a lower dimensional representation, and then another linear transformation to get back out to your high dimensional representation. So a deep autoencoder would just be replacing those transformations with neural networks. And you can just use kind of the same multi-layer perceptrons that we were talking about. So let's imagine you have an input image, some hundreds of dimensions. You want to compress that down to some lower dimensional representation. And then you want to blow that back up to your high dimensional representation. So this is how an autoencoder would work, where this is often called the latent representation. And so previously what you were doing would, like this kind of encoding stage was just a linear transformation, so matrix multiplication. Now you can just take like the multi-layer perceptrons that we just talked about and use that for an encoder, use that also for a decoder to blow back up to high dimensions. I should just mention, I'm using this for intuition. In practice, for an image, you would probably not be using like a simple multi-layer perceptron. You'd probably add like convolutional layers just to be a little bit more efficient. But anyway, just to show you that kind of this works. So the encoding network, its job is to take this high dimensional representation and compress it down. And then the decoder has to reconstruct that input data from the compressed representation. And so again, we're starting with randomly initialized networks. When you start this, the output is just complete garbage, right? But the two networks are kind of working together. In order for the decoder to be successful, the encoder needs to properly kind of compress this down into an informative latent representation. Does that make sense, everybody?
Sorry if I'm confused, but the output layer here, you're not classifying anything, so there's one node.
Yeah, sorry. Yeah, that's my fault. This should really be, the output dimensionality here should be the dimensionality of the latent representation, and the dimensionality there should be back to your input. I'm sorry about that. That's my fault. But yeah, so we've gone from like a classification problem where you have data, and each data, like each image was labeled like this is a 3, this is a 6. So that's a supervised machine learning problem, right? And this is an unsupervised problem where you don't need any labels for this data. So like you've got an image, you could run this network without knowing what's in that image. The network doesn't need to know. It's just trying to find an informative representation. So unsupervised learning, for linear problems, you'd use often something like PCA, principal components analysis, or factor analysis. Autoencoders are a pretty powerful nonlinear unsupervised learning method. Okay. So again, just trying to build some intuition here. So what's going on here is that by limiting the dimensionality, we're forcing a compression. So let's imagine you had a 1,000 pixel image. If your latent space was 1,000 dimensional, then your network probably wouldn't do anything. Like to reconstruct accurately, just pass the data all the way through, right? Just multiply by ones as you go through, and you get perfect performance on this reconstruction, right? So the kind of power of an autoencoder is this is restriction, right? This bottleneck in the middle that forces these networks to find informative representations, right? The only way this pair of networks can be successful in reconstructing, because you've gone from 1,000-ish, maybe thousands of dimensions down to a handful. The only way you could reconstruct those 1,000 dimensions is if you learned a very informative compressed representation in the intermediate stage. And so again, as we were mentioning, this is a completely unsupervised problem. There are no labels on this data. And so how is this useful? So in a lot of applications, like an autoencoder, denoising autoencoders are a common application where maybe your image has noise on it. If you're learning this compression, well, that noise is like varies independently, across your different images. This encoder would effectively learn to throw out the information about the noise because it has to compress the data, has to be able to reconstruct accurately, and it simply can't store enough information to reconstruct the noise accurately. So effectively, one application of autoencoders, and so what we'll be talking about this afternoon for neural data is using autoencoders effectively to denoise your data. By forcing a compression, the encoder has to pick, like what am I going to keep about the input, and it cannot keep the noise because it just takes too many dimensions to represent, so it typically throws that away. And then last, just for some intuition as you go to Eva's lecture tomorrow, the decoding model is going from the latent representation to generating the data itself. So you could think of this as a generative model, meaning it's trying to generate the data. Yeah, please.
Just a quick question regarding the denoising.
Yeah.
So do you have some theoretical mathematical intuition of how this encoder can be associated in terms of noise or signal, but it is unlabeled anyway?
Yeah, I'll give you some intuitive intuition, which is how I typically work on things. So let's imagine you had a bunch of images. So I'm not mentioning that, when you're training these types of networks, you're talking about, many hundreds of thousands to millions of examples, right? If you looked across that data, there are certain features that would be common, right? Noise would not typically be common. If there are shared noise features, then actually the encoder would probably keep those, right? If there's some artifact that shows up on every image, the encoder would say, oh, that's a really useful feature for reconstructing my data, I better keep it. But so basically what you're assuming is that some properties of your data are independent across different examples, are not predictable, and so noise in this case is not predictable. And so that effectively has to be thrown out because there just isn't enough, because of this bottleneck, you can't keep all that information.
And the output from the encoder, is that kind of compression or the latent representation meaningful? I mean, can people use that to try to infer, what the network has learned and how it has kind of segmented?
In some ways, so let me just skip forward to a couple other slides just to show you. So let's imagine you were back to our kind of MNIST example before we talked about it in the supervised case where you had labels for each image. What if you just ran these handwritten digits through an autoencoder? And there's a really cool blog post where they actually do this. Literally, just write out the same networks that we've been talking about. It's like, I don't know, 10 lines of code maybe to do this. And then let's look at that latent representation that's learned by the network. So we're randomly initializing the network. This isn't an exact diagram. Again, the dimensionalities are, at the input, it's the number of pixels. At the output, it's the number of pixels. In this specific case, the latent dimensionality is 2, just so we can visualize it really easy. But this wouldn't be like a high-performing network. Anyway, so when you start out and you look at the latent dimensionality, here are the colors of the different digits. It's randomly initialized, so you should expect it to be complete garbage, right? Like it's just, collapsing everything into a little cloud. But over the course of training the neural network, you can start to see that in order to successfully reconstruct the input data, it effectively has to learn a latent representation that separates out the different types of data, right? So again, the colors are the different digits, but you can see it's very clearly learned structure in the data. There's one thing I'll mention, which they go over in this blog post. This isn't exactly what we're talking about. This is a variational autoencoder, which there's so many things I can't go into detail in an hour lecture. But if you're really doing something like this in practice, you want to use variational training methods rather than just the intuitive method that I told you earlier. But it's only kind of a minor difference.
A related question.
Yeah.
So let's say we take this latent representation and I perform now PCA on the raw input. Would those give me the same output?
If you looked at PCA on the image data.
Yeah, with
right.
2 dimensions, 2 PCs.
Yeah.
And compare that versus yours.
Yeah, no, this would be, I think, much more informative because, think back. So PCA can only do kind of linear transformations.
Yeah.
So think back to that problem when we had the point cloud and the curved data where, PCA would not be able to separate out those data. It's similar here, but now we're talking about 784 dimensions rather than 2, but it's still separating these data in the original space is like a nonlinear problem. And so PCA wouldn't really stand a chance of, I mean, you might get some like rough structure, but not great.
The problem is I guess the classes here is also like 10. And I guess if it is do binary classification, it might be a bit sooner. Is that situation?
Maybe. I still think for PCA, probably not, because it's unsupervised. So it doesn't know anything about the actual labels or anything. It's just trying to say, like, if I could pick one dimension out of these 784, what preserves the most variance in the data, right? So that might not have anything to do with the best classification dimensions.
Right.
So if I were to try to, interpret this in terms of similarity, it looks like 9 and 4 are kind of in the same space. Is that
right?
Because they look similar?
It's a good question. I'm not really sure, but my guess would be, yeah, like a 9 and a 4 do look pretty similar. And again, like in practice, you wouldn't use only 2 dimensions. So like if you had more, they would probably, like the 9 and 4 would probably separate out. Maybe to get at that a little bit more, in the same blog post, they actually kind of look at this latent space and said, okay, if I just pick kind of values in a grid in this latent space, and then just use kind of the decoder part of the model, so generate out to the high dimensional space, what does the reconstruction look like? And you can kind of see this smooth grade, continuum of numbers, and you can kind of see in the middle where they get blurred together and that sort of thing. Make sense? Yeah, please.
Two dimensions, 2 neurons for the latent representation in this case. Do you get to compute the number of neurons you have in the latent representation or not?
Yeah, so the number, exactly, then that like latent representation, it's just a parameter that you would set when you're kind of coding out your network. So you could have easily picked 4, 10, and it would have run like, exactly the same. It probably would have been a much better solution. So there is a tricky thing there, which is like, okay, how do you pick that parameter? But, at the input stage, we're talking about, in this case, 784, typically, a very high dimensional. So there's like a lot of room there where you can kind of, try different architectures, like slightly change that parameter setting and see how that affects your classification performance or whatever, your reconstruction performance, whatever task you're trying to do. So sorry, in this case, reconstruction performance. Or another thing you can do is use one parameter with, like, maybe use something that's high dimensional. I'm just going to make something up, like 50 or 100. But then do what's called regularization, where you would set, you would make the network pay a penalty for using a higher and higher dimensional representation. So you can give it the capacity to do more, but penalize it for using it. And that way you could just use one architecture and it'll like still, if it only needed, a few dimensions to solve the problem and you gave it 50, if you kind of tune regularization properly, it'll favor the lower dimensional solutions.
So the method you described just now is kind of an optimization where you can use to get a good number of dimensions per reconstruction.
That's right. Yeah, so that's what we typically call a hyperparameter. So parameters are like the weights of the network that you're learning, whereas hyperparameters are kind of like these meta choices that you make, like, dimensionality of a certain layer or regularization strength or something like that, where the hyperparameter optimization is a huge field in and of itself also, but yeah. Okay, we all good? Yeah, please.
Repeat this process multiple times with different initial parameters, do you always get the same
Right, good question. So I think you'd probably get latent spaces with similar properties, but there's some things that are like not meaningful here. Like you could imagine rotating this latent space and it would perform the exact, so it's like, if you had your encoder network and it was doing a rotation, the decoder network could also do a rotation to kind of correct for that. and it'd have the same like reconstruction accuracy. That's kind of one of those, like we were just talking about, like parameter values that have like similar performance, like similar reconstruction loss, but different ultimate solutions. So there are things like that where you certainly wouldn't literally get the same latent space. You'd likely get something that has similar properties, I think. So I think we're pushing 10:45. Yeah. Yeah.
But the one last thing I wanted to mention about reading is I will upload a notebook that walks you through how you can build your own DAUs someday. So you will have code to play around with this should you want. So you can build like this example, but it's going to use, so I also put that this on the file today. So it's going to use kind of the similarities between both of us. You don't have how
Great. Yeah. Cool. All right, so we're now getting to topic 3. I'll try to step a little bit more quickly. This is completely different now. This is now we're talking about more neuroscientific concepts rather than machine learning. And in the afternoon lecture, we'll kind of combine these together, right? So autoencoders that I just talked to you about, and neural population dynamics, which I think Anne covered a little bit in her lecture last week. But so I want to take a second I know there's like a variety of backgrounds here. So if we just think about like the types of data that we'll be talking about today, that you guys will be using in the collab notebook today, are intracortical recordings. In this case, from monkeys doing reaching. So some of you are probably well familiar with like intracortical microelectrode arrays. This is a Utah array. You can see kind of a thumb in the background there for sense of scale, so they're pretty small. This one has 100 electrodes. Each of them is about 1 millimeter long. So they go, they're penetrating. They go into the brain, but only at the depth of about 1 millimeter. And when we use these in electrophysiology, these are the types of signals that we get. So we had 100 electrodes, so there are 96 electrodes. There are 96 channels there on the screen. And as the monkey's reaching, we can pick up the activity of individual neurons. This isn't a particularly good recording, so you don't see kind of well isolated neurons here. But that's just to give you a sense of the types of data that we're talking about, the scale. So we're talking about, for this lecture and for the demo this afternoon, at the level of individual neurons, populations of individual neurons. Does that make sense? Okay, so I'll define some terminology that's going to be useful later. So when we talk about neural population state spaces, here's what I'm getting at. Let's imagine that you're recording the activity of 3 neurons. Neuron 1, neuron 2, neuron 3. You could describe the activity of those neurons in a 3-dimensional space where the axes here correspond to the firing rate of any individual neuron. So neuron 1 is on this axis, neuron 2 on this axis, 3 on this axis. That means if I looked at the activity of the neurons at some point in time, let's imagine that I smoothed it or looked at the number of neurons over a certain number of spikes over a large window to try to estimate the firing rate. The firing rate of these 3 neurons represents a point in our 3-dimensional space. So when we think about like a neural population state space, what we're saying, like if we kind of go through at different time points, that the state of the population, this is a simple 3D example, but the state of the population is represented as a point in our 3D space. And this empirical finding that's been repeated many, many times is that activity doesn't kind of uniformly fill this space, right? If you record from these 3 neurons, and you think about all possible combinations of firing rates, that would kind of occupy this entire 3D volume. Empirically, we don't see that. So what we usually see is that activity is confined typically to some like lower dimensional representation, or lower dimensional, we can identify kind of structure that's shared. The neurons aren't acting independently. So this is what we'd call a subspace, like just like if you have a 3-dimensional space and have a plane within that 3D space, that would be a subspace. Sometimes people refer to this as manifolds. We had a long conversation about that last night, and I understand you guys were talking about manifolds last week. That terminology is maybe a little bit loose, but so if you're taking a linear transformation, this would just be a subspace. The key point is, activity is often confined to lower dimensional spaces within your high D space. This is like a 3D example, but typically we're talking about hundreds of dimensions that we can record simultaneously. With modern techniques, you can get to many thousands of neurons simultaneously. That's a pretty big space, right? A 10,000 dimensional space. But activity isn't just kind of like uniformly sampling that space, but it's often confined to lower dimensional representations. This is the same thing. Sorry about that. I duplicated the slide. So that's all fine. I think you've covered that before. But when I'm talking about dynamics, what I mean is kind of going a little bit further than this. But it's not just that activity is kind of confined to lower dimensional representation or lower dimensional, let's say, subspaces, but there are stereotype patterns in how the activity evolves over time, right? So activity isn't just zipping around randomly in this space, but it kind of obeys rules, that's what we refer to as dynamics. So if you have your neural population state space here is 2 dimensions, so if you represented that by a variable, it would be a 2-dimensional variable S. So when we talk about dynamics, like what we'd be talking about is the change in state as a function of time, so ds dt. And for a system that was kind of completely predictable, like this vector field that I've drawn here, I can't get my mouse. Like this vector field is just saying, like, at each point in state space, how is activity evolving? So it's pointing in the direction the activity is going to evolve over time. So that's just the change in state as a function of time. So that's just a graphical depiction of this dynamics equation. Everybody good with that? Okay. I'm going to very quickly step through a dynamical systems example, because again, I think like building intuition for this stuff is really important, like way more critical than going through, well, in my opinion, going through the math. But so let's imagine you had a 1-dimensional pendulum. So just like a pendulum that could swing back and forth, and you kind of started it at one position and let go. So you could plot out the position of that pendulum as a function of time. For small perturbations, it would just be a sinusoid. Kind of starting low, swinging forward, going high, blah, blah. You could also plot out the velocity as a function of time. So initially, you're holding it, velocity is 0. You let go, and it gets positive. It reaches a maximum in the middle. It goes to the other side and gets to 0, and it's going to swing back and forth. So this oscillating pendulum has a sinusoidal position and velocity, and if you just know those 2 variables, you're completely capturing the system. Okay, so all you need is the position and velocity to describe what this system is doing. All right, why am I talking about this? So that's a 2D state variable, x. Let's imagine we had position on one axis and velocity on the other axis. If we plot this as a function, if we plot these against each other, letting go of the pendulum here, you would kind of see this trajectory, like this curved trajectory. But maybe let's take a different point, start at the other side, do the same thing. So we've got sinusoidal position and velocity. Plot that, and that's just kind of a rotate, a little curved path starting from another point. So the key here is, think back to what I was saying about dynamics. That's relating the change in state as a function of time to the current state. For this system, that would just be this rotational dynamics, so the vector field that you're seeing here. Okay, so meaning I showed you 2 examples. We could pick any kind of position and velocity to start the system and let it run. And this dynamics equation would completely capture what the system would do, minus like friction and whatever out to infinity. Okay, it's just going to sit there kind of oscillating. Does that all make sense? Okay, all right. Key thing to get across here is just that dynamics are a way of relating the current state of a system to its future activity. And they're a really useful way of thinking about neural systems as well.
I have a question.
Yeah.
Again, the previous thing you showed about how when you're recording from an area in the multi-brain, you see that the activity of the neural cell does not explore all the space, it remains limited. How far does that spread? Like, okay, you're in a specific part of the brain, it does that. If you were to look a bit further away, I presume that falls apart, or it doesn't? Like, I don't know, is the whole brain just...
Right. Yeah. No, that's a really good question. So if you think about kind of like classic views, let's say of a place like an area like motor cortex, you would assume that it's like nice and segregated. So like maybe there's specific parts of motor cortex that relate to finger movements and wrist movements and whatever. But like they're, as you go like from more medial to like more lateral along motor cortex, you go from like feet to fingers and to like speech and stuff. Anyway, in like a nice gradient. Key point there is like there's clearly like differences, right? Like there's region differences. There's also like some overlap. So like we see like representations of different movements kind of throughout. Like even if we think we're recording in a hand area, we might see some activity that seems to be related to speech or related to foot movements. So there's a lot of distribution as well. To get to your point, like I think it's not clear. So when we see these like low dimensional representations, how much of that is just a product of the fact that we're only recording from this system in, like the monkey is doing a specific task. And if we were to do like 100 other tasks or like go through its activities of, walking around its cage, does the dimensionality change? I think likely it does. Like, it's so to some degree a constraint of the way we're probing the system, like the data that we're collecting. But on the other hand, we're talking about a network that's like, millions of neurons. And I don't think the dimensionality is in the millions. I think, the dimensionality is maybe in the hundreds or something. So even if you did like complicated tasks, the activity would be confined to much lower dimensional spaces than the full kind of possible activity. Does that make sense? Yeah. So I mean, I don't think we have the data to answer that, but I would be shocked if we record from a monkey's brain for a year and it's like a 1,000,000 dimensional space that gets mapped out. Oh, sorry, I should say there's some good literature on this, on high dimensional representations, especially in like visual cortex, from Carson Stringer and Marius Pachitaru, where they can use calcium imaging to probe like 10,000 neurons simultaneously, and it seems there that activity is fairly high dimensional. I mean, still not. I mean, I don't think it's still kind of occupying the full space, but that is one of the cases where they were able to kind of do the experiment, test it with like a bunch of different visual images over long recording times, and see that activity is fairly high dimensional.
So part of my question is that as you're moving in different brain areas, presumably the manifolds change.
Right.
Say,
Yeah.
Right. But as far as people have looked, there are these manifolds that pretty much everywhere they have looked. Or like is there like a piece of the cortex or?
I'm trying to think. I can't think of good counterexamples for like low dimensional structure in neural activity. I mean, like, some things are fundamentally high dimensional, like the retina, conveying visual information. I mean, the visual scene is high dimensional. So I think, the closer you get to like primary or like early sensory areas, for sure things are high dimensional. But yeah, I don't know. Chris, do you have any thoughts on that?
The motor cortex is inherently controlling the arm, and the arm only has 40 or so muscles and like some order 100 channels of sensory information. So like you're sort of bounded by the biomechanics, like how many dimensions you really expect it to be there.
Yeah. I mean, we see similar things in like somatosensory cortex. We see similar things in cognitive areas like dorsomedial frontal cortex. But again, could be the task. We see this a lot, that activity is low dimensional. Sorry, I did not have a better answer. Yeah, so it's 11. I think I'm going to save some more details on dynamics to start out the methods lecture, if that's okay, to give people a bit of a pause here.